All right, 8.4, the first derivative test. I gotta tell you guys, this is like one of my most favorite things about calculus. I just find it really fascinating how you can analyze a function using calculus. So let's talk about it a little bit. Remember that we said in the last video that when you get a derivative of 0, when the derivative is 0, that's when you get these horizontal tangents, and those are candidates for minimums and maximums. Also, we can also see that the derivative changes there, right? The derivative is going to go from a negative value or a value less than 0 to a positive value, and that means that we're going to going to have a min. So a way to kind of think about that, we're going to make some tables, and a way to kind of think about that is if you have a derivative that goes, at some x value, it goes negative, 0, and then positive. That means it's going down, flattens out, and then goes back up. So that's obviously a min. And conversely, we could have a situation like this where the derivative is some positive value, then it hits 0, and then some negative value. So that means it's going up, over, and then down. And so that is obviously a maximum. And then we could have one where it's positive on both sides or negative on both sides. And so that just means the graph kind of temporarily flattens out, right? So if it went negative, 0, and then negative, that means it's doing what it did here. It went down, zeroed out, and went back down. And it could also go positive, 0, then positive, and that would graph would look something like this. It would look like it went up, over, and then up, right? And that can happen in a graph as well. So it means that just because it's at 0 doesn't mean there's necessarily a max or min. It just means that it's a candidate for max or min, because you could have this situation as well. So it's more about what happened right before and right after when we look at the derivative. Let's take a look at some examples so we can kind of see how to do this. Okay, again, this is some of the notation that we're looking for, right? If the derivative is greater than 0, then that means the derivative is positive, and that means it's increasing. So the function is going up. If it's less than 0, the derivative is negative, then that means that it's decreasing. And if it's 0, then that could be a max or min. It's a critical number at least. So that's going to be one of our first steps, is just find the critical numbers. And so this is kind of what we call a pre-example for example 1. We're going to do this first, and all I want to do is find the critical numbers. So what does that mean? Well, that's when the derivative so critical numbers is when the derivative, I'm going to put this down, it's important to remember, either does not exist or it equals 0. So let's first just find the derivative. The derivative of this would be 2x plus 8. Well, there's no reason for this derivative to not exist. It's just a linear function. But there is a time when it equals 0, and so we could find that. We just set this thing equal to 0, and we do some algebra. So that'd be 2x equals negative 8, and then divide by 2, you get x equals negative 4. And so that is my critical number. Cn there stands for critical number. X equals negative 4. So let's remember that. My critical number is x equals negative 4 as we go to the next page. All right, so I already found that my critical number is x equals negative 4. That is important. The way that this table is kind of laid out here, I don't really like it that much, so I'm going to kind of add to it here. So let's include some of our x values, and let's think of this as kind of a table like that. You can kind of ignore these little hashes here, because what you're going to want to put in the center is your critical number. And this one just has 1, so it's a relatively simple one. So we just have negative 4. And then what we do is we want to think about values of x that come after 4, or after negative 4. And for this one, it's just all the way to positive infinity. And values that come before negative 4 and all the way to negative infinity. That's an infinity sign. Okay. What are some values, some good values to think of there? Well, I would actually just choose negative 5 here. But to the right of negative 4, I could choose negative 3, but I think an even easier value to plug in and test there would be 0. So these numbers on top, these are just a value that I'm choosing to test for this location and for this location. And we actually already know something about negative 4. We got this because that's when the derivative equals 0, so we can go ahead and put a 0 there. And now we're going to test these other values into the derivative. We'll fill this thing in. We don't really need this. This doesn't really matter, and this doesn't really matter. But this might matter because this might be the max or the min of a function. So And judging by what this function is, that it's just a parabola that's opening upwards, you can kind of determine that this is going to be a min. So we can kind of make some predictions what the derivative is going to do. But let's just do the math so we can see it. Okay, we already took the derivative on the last page. We said that it was 2x plus 8. And so what I want to do is I want to test these values. And this negative 5 represents all values from negative infinity to negative 4. Right before negative 4, not including negative 4. So let's just use negative 5 as a test. So if I plug in negative 5, I get 2 times negative 5 plus 8. That's negative 10 plus 8. That's negative 2. Now, I don't really care about the value. All I care about is whether it's positive or negative. And this is negative. So I'm going to put a big negative sign there. Okay. Now, let's test the value that's to the right. And I chose 0 because I thought that'd be the easiest one to plug in. So let's do that. The derivative at 0 equals 2 times 0 plus 8. Well, this is clearly just 8, which is a positive number, so we could say that to the right, the derivative is positive. And we can be certain that it's not going to change because there is no other time when the derivative equals 0. So if it's positive, in order for it to go back to negative, it would have to equal 0 at another point in time, but there isn't. So we know it's going to be positive forever as we go in the positive direction of x, and it's going to be negative as we go to the left of negative 4. So that's pretty straightforward. So when is f is increasing? Well, we know when f is increasing, it's when the derivative is positive. And so we're just going to say the interval from negative 4 to positive infinity. When is it decreasing? Well, it's decreasing from negative infinity to negative 4. Our critical number, we know what that is. That is when x equals negative 4. Do we have a relative max? No, we don't. If we think about this, I'm going to try and draw a little sketch. It must be going down, flattening out, and then going back up. So there is never a time when there is a max. So I'm just going to say NA, or does not exist. And then finally, do we have a relative min? Yes, we do, because we can see clearly it went down, zeroed out, went back up. That is a minimum. And so we can say, yes, it is at x equals negative 4. And what is it? What is it? Well, we could plug into the original function and figure that out. Here's the original function. Let's do it down here. What is y of negative 4? Well, that's going to be, let me do parentheses here. Negative 4 squared plus 8 times a negative 4, running out of space, plus 10. Negative 4 squared is 16. 8 times negative 4 is negative 32, plus 10. That's positive 26 and negative 32. That's a negative 6. And so we could say that f of, well, this is really y, but f of negative 4 equals negative 6. And so that is the relative minimum, and it happens at x equals negative 4. Okay, that's a relatively simple one that we can dissect using calculus, but let's get into some ones that are a little bit more fun. Okay, here we have a cubic function. Same problem though, same process here. The very first step in this is to identify my critical numbers. So that means I need the derivative. Remember, critical numbers are when the derivative equals 0 or it does not exist. So take the derivative. Y prime equals 6x squared plus 6x minus 12. We set this derivative equal to 0. If I set this derivative equal to 0, again, there's no reason why this wouldn't exist. It's just a parabola. If I set this equal to 0, I could divide everything by 6. And so then I would get that x squared plus x minus 2 equals 0. I could solve this a number of ways. I could use the quadratic formula. I could complete the square, but I think the easiest way to solve this is just going to be by factoring. And it's a simple star method factor. I need something that multiplies up to negative 2 and adds up to 1. I got 2 and negative 1. So that means my factors are x plus 2 and x minus 1. And that means my zeros for this thing are what would I plug in here to make it 0. So I could say that this function is 0 when x equals negative 2 and positive 1. It's going to be the opposite of your factors every time. So this one actually has 2 critical numbers. All right. So that changes something about how I'm going to make this table over here. Remember, I'm going to add an x row up here. Let's think about this. I know that I'm going to have, let's see, I'm going to make a line here. Because I know now that I have -2 is a critical number and +1 is a critical number. And I already know now that that's when my derivative equals 0. So I'm filling some stuff in, as you can see. And remember, I care about values between here, and I care about values afterwards, and values before -2. Kind of running out of space. All right, so next what we need is we need some values to plug in for these intervals here. So what's something that's less than -2? Probably a good value is just -3. What is something that's between -2 and 1? Well, probably a really good value to plug in there would be 0. And what's something that's greater than 1? A nice easy value to plug in there would be 2. So we're going to, again, we don't really care about the function heights here, here, or here. But we do care about here or here because these could be maxes or mins. Now, we need to evaluate whether or not these three locations are positive or negative using the range or the values we chose to represent those intervals. So let's do -3 first. We're just plugging it into the derivative, and we want to plug it into the original derivative. And honestly, I'd use a graphing calculator for this. I would plug this value into my calculator and then use the table function to just plug values in really quickly. So I'm going to do that off to the side of my calculator. I'm typing in 6x squared plus 6x minus 12, and I'm going to my table feature, and I'm just going to plug in -3. And when I plug in -3, I get 24, which tells me this is positive. Now, if I didn't have a calculator or this is a non-calculator question, I could just go ahead and do all the algebra here, just plug in a -3 and work it all out. But since I'm plugging it in it frequently, it makes sense to just use a calculator to do this. When I plug in a 0, I get -12, so this is negative. And when I plug in a 2, I get positive 24. So this is positive. So that tells us about this graph. It means it's going up, flattens out, goes down, flattens out, goes up. All right, this is really informative. Let's take a look. So when is f? F is increasing on 2 intervals. We can see that it's increasing from -infinity to -2. And sometimes you'll see like a little U here for union. It just really means and from +1 to +infinity. And it's decreasing from -2 to +1. Critical numbers, we had 2 of them. It was when x equals -2 and 1. Relative max. We could tell from our sketch now that we have a relative max here at x equals -2. So we could say at x equals -2, and f of -2 is what? Well, we can just plug a -2 into our function. Again, I would just use a calculator for this. No reason not to. Again, unless they say, you know, you can't use a calculator. But so I'm going to plug in 2x cubed plus 3x squared into my y equals minus 12x. So I'm just plugging in this original function. I'm going to my table, and I'm going to plug in a -2, and I get 20. So f of -2 is 20. And for the relative min, I know that's at x equals +1, so I'm going to use that table feature again and plug in a 1, and I get -7. So I know that f of 1 is -7. And so I was able to find quite a bit out about this function using the derivative and the critical numbers. All right. Pretty exciting stuff. We'll play with this a little bit more when we go to 8.5, the second derivative test. But for now, this is pretty good. We're just trying to find the critical numbers and use that to find the relative or absolute max and min. See you guys on the next video.